For the pressure wave in the sound wave, pressure oscillation in the sound wave, we can see that quite obvious if we look at this figure again. We can see that when the undisturbed gas displaced and compressed, when the sound wave passes through this point, the volume of the gas decrease. So it means that the pressure, the local pressure of the gas here will increase. In contrast, if the gas here or the medium here expand when the sound wave pass through, so we will have that the pressure, the local pressure will decrease, and we can have the oscillation of the pressure of the medium. And now it's better, this picture is better because you can stay at a particular point. For example, if you look at the pressure of the medium at the point X here, and you can observe the change of the pressure here, and it's not confused. It's not like when you observe the displacement of the medium, because if you observe the displacement of the medium, you have two kind of position. That is the position of the medium and the displacement of the medium itself. But for the pressure, you can observe the variation of the pressure at a certain point. So when the sound wave passes through the medium, the pressure will increase or decrease, or we can say that the pressure will oscillate as because the medium is compressed or expand. And if we write down the pressure wave, we can have the mathematical wave function for the pressure wave like this. P, or we may say delta P is delta P max sine kx minus omega t. We will see soon that if we use this form of the pressure wave, we may have to change a little bit the form of the displacement wave, but that is not important because we can choose each wave. Like if you want to explain it in terms of the displacement, you can use this form. But if you want to explain the wave in terms of the pressure, you can use this form. But if you use this form of the pressure wave, the corresponding displacement wave will change the form a little bit from this. Okay, so let's see. Here you can see that we use the symbol delta P here. We use the symbol delta P here to show that this is the change of the local pressure of the medium from the pressure of the undisturbed gas. Okay. If we look at this figure again, for the undisturbed gas here, you may have the pressure, and we may call it the P0. That is the pressure of the undisturbed medium or undisturbed gas. And when the sound wave passes through, the pressure, the local pressure of the medium change. so it may change to be P. Okay, if the medium is compressed, P is greater than P0. So we will have that the change of the pressure is equal to the P minus P0. Okay, the change of the pressure is P minus P0. Okay, now we can say that P0 is like an equilibrium configuration. Like if we look at the mass spring system, the equilibrium position is the position at that the restoring force is equal to 0. In this situation, we can set the reference point or the equilibrium configuration as the configuration that the medium has the pressure, the local medium has the pressure equal to that of the undisturbed medium. So the change of the pressure will oscillate at the sinusoidal function. So we can write down the pressure wave like this. Okay. We can show that this pressure wave is related to the displacement wave as follows. From the relation between the change of the pressure, the bulk modulus of the medium, the change of the volume and the initial volume of the medium, we have that delta P is the change of the pressure is equal to the minus of the bulk modulus of the medium times the change of the volume of the medium over the initial volume of the medium. This is a general relation. Now, if we look at the medium in the cylinder that the sound wave pass through, we have that initially when the gas is undisturbed, if we look at the element of the gas of the thickness delta X and has the cross-sectional area of A. So we have that Vi is equal to A delta X. Okay, and when the sound wave pass through, this element can be compressed. Okay, so we may have that the thickness of the element may change to delta S. The cross-sectional area still the same because we look at the one-dimensional wave in this direction only. So the compression is on this direction only. So we have the cross-sectional area still equal to A. And we have the change of the volume of the medium equal to delta V is equal to A delta S. Okay, this is quite obvious. If we look at this figure again, you can see that the displacement of this element make the element of the medium move to this position. You can see that this phase of the element of this element move with the displacement. You can say that it moves with the displacement S1, and this phase move with the displacement S2. Okay, so the change of the volume is equal to the S2 minus S1 times A, but here we define S2 minus S1 as delta S, so we have that the change of the volume is equal to